Okay, let us start. Okay, and so most of the algorithm we will see later in this course will be randomized algorithm. So we need to revise some basics of discrete probability, and we will see one example which is randomized quicksort. And so in this talk we will revise those topics, and we'll continue with the randomized techniques tomorrow as well. So first, basics of discrete probability. So we will be dealing with for the algorithm design, we will be mostly dealing with discrete probability. What do I mean by discrete probability? Like the probability space is a pair, it has one set. That set contains that set is a set of elementary events. So each element in that set is called an elementary event. And we say that a probability space is discrete if that set is a countable set. Okay, one of the example of a countable set is like a finite set. Okay, most of the time we will be dealing with finite set. Okay, so even if it is countable set, it is discrete probability space. Okay, and then there is a probability function. Every discrete element you will be mapping to one number between 0 and 1, such that the sum of the probabilities will be equal to 1. Okay, just see simple examples. You just toss an unbiased coin. So what is the probability space here? The set. How will you define it? It is the set omega is head comma tail, and the probability of getting head, probability of getting head, both are equal to 2. I'm audible, right?
So you are.
Okay, thank you. Okay, now take the second example. You just throw a 6-sided unbiased die. Unbiased means equal probability for getting any of the sides. Okay, so then you can define the set of elementary events to be 1, 2, 3, 4, 5, 6, and getting any one of them, any one of those numbers when you throw a die is 1 by 6. Okay, now here is the one. Okay, you just throw a pair of independent dice. So you throw 2 dice. Then how will you define probability space? Anyone want to say?
Can you please repeat?
So the random experiment is throw 2 dice, independent dice, like die 1, die 2. Okay. Now for this random experiment, how will you define the sample space or probability space? So notice that probability space is a pair containing elementary events and probability. Correct. All possible 36.
So shall be 2-dimensional.
But your voice was breaking. Yeah, somebody wrote it in the chat. Okay, that is correct. Okay, it's actually like pairs of numbers ij, where I and j are integers between 1 and 6, and the probability of getting any one of them is 1 by 36. Okay. Now, what is an event? Event is a subset of this omega. A subset of this omega is called an event, and the probability of getting that event happening is summation of the probabilities of the elementary events in that event, okay, in that set. Okay. And complement of an event is denoted by a bar, which is actually the set omega minus a, and that is also an event. An event is a subset of omega, okay? And probability of that event happening is summation of the individual probabilities within that event. Okay. Now suppose I can define event like look at our previous example, throwing two dice, okay, independent dice, okay, and then I can define A to be the event that the sum of the two numbers ij should be even. Then like so A can be defined as I comma j such that I plus j is even. Now if you sum it up all of them, you will get, half of the time you will get even number. So probability of A equal to half. Okay. Now there is a notion of independent events. Okay. Two events A and B. For this event, A is a subset of omega and B is a subset of omega. Okay. Two events A and B are independent if and only if the following hold. Probability of A intersection B, like what do I mean by A intersection B? Look at the set A intersection B, and then that has a probability. What is the probability of that set? Like summation of the elementary probabilities, which is part of the A intersection B. That should be equal to probability of A times probability of B. Then we say that A and B are independent events. Okay. So, and if that is not true, then A and B are dependent. Just take a simple example. Okay. Coin to toss two coins. Okay. And they are unbiased coins. So the sample space is head, head, tail, tail, head, tail, tail, head. Okay. And the probability of getting any one of them is 1/4. Notice that here the elementary event is HH is an elementary event, TT is an elementary event, like that. Probability of getting any one of them is actually 1/4. And now let A be the event that the first coin is head and B be the event that the second coin is tail. Okay. Now, like when you throw first, after you like when you throw the first coin, what comes up is head, and then the random experiment, like the second coin when you throw, that comes up tail. Okay. Now, what is that? If A and B are independent event, if you notice that what is A intersection B? A intersection B is like in the first place you get head and in the second place you get tail. And you can see there is only one such a thing. This is actually this one, right? Head and tail. Okay. Like first head and that probability of happening is 1/4. And probability of head is 1/2 and probability of tail is 1/2. Like probability of A happening. What is probability of A? The first coin shows up head. The second you doesn't care. That is actually 1/2. Like head, head and head, tail. Similarly for B, the second is tail. First you don't care. That is also like 2/4, which is 1/2. So you will get that, left hand side equal to 1/4, right hand side is equal to 1/4. Left hand side and right hand side of this. Okay. Now comes the second one. So these are independent. Now look at this event. Okay. A is the event that both are not tails, and B is the event that second coin is head. Is this independent? Both are not tail. A is the event that both are not tail, and B is the event that second coin is head. Is this independent? What do you think? They are dependent. Okay. Now, what is the reason? So, notice this. A is the event that both are not tail. What is that event? This one will be there, this one will be there, this one will be there. Okay. And B is the event that the second is head, which all that second is head, this one and this one. What is A intersection B? A intersection B is only one element in it. H comma T, HT. Okay. First is head, second is tail. And what is the probability of happening that? 1 by 4. And what is the probability of A? A is 3 by 4. What is the probability of B? That is 2 by 4. So 3 by 4 times 2 by 4, which is actually 6 by 4. On the other hand, probability of A intersection B is how much? Sorry, not 6 by 4, right? Yeah, so you will get that number. Like what is the number? 3 by 4 times 1 by 2, right? Yeah, 3 by 4 times 3 by 8 on the right hand side. And in the left hand side, what you get is actually 1 by 4. They are not equal, so they are dependent. Okay. So this is the formal definition. But in the first example, you will see that, tossing the second coin does not depend on what comes from the first coin. Because of that, you can easily infer that they are independent. Because the first, look at the first example where, A gives the first is head and B says the second is tail. So A depends on the first coin and the B depends on the second coin, and they are, independent. Okay, that way also you can infer, right, in many examples. But otherwise, you need to do this calculation. Okay, let's move on. Okay, so they are dependent. Okay. Oh. And there is another notion which is called, union bound. What is union bound? Probability that A union B is at most probability of A plus probability of B. Okay? And if you write the set notation, like what it is, Venn diagram kind of thing, that will be very obvious. Okay. Okay. Now, what is a random variable? Okay. A random variable, given a probability space, a random variable is defined over a probability space. What is a random variable? It is a function that maps every elementary event to a real number. So, random variable is just a function. And now we need to talk about expectation of a random variable. Expectation of a random variable x is defined as, so x is a function. Okay, summation small omega in big omega, that means small omega is an elementary event. What is the probability that what is the probability of small omega happening times x of omega? X of omega is a number, right? X is a function, so x of omega times probability of omega, summation over all small omega. Okay? So expectation is the average value of x according to the probability, according to the weight given by these probabilities. Okay? Just quickly see a couple of examples. You just throw a unbiased die, so the sample space contains in the sample space the first element is a set, that is omega. That omega contains 1, 2, 3 up to 6, and the probabilities are defined to be 1 by 6 for each of them. And suppose you define x of I to be I mod 2. What does it mean? It will be 0 if it is even, and 1 if it is odd. Okay. Then expected value of x, you can write like I going from 1 to 6, probability of I times x of I, and you will get, half, which you can think that, half of the time you expect an odd number shows up and half of the time you expect an even number shows up, right? And now suppose you define random variable that y of I is equal to I. So which is actually saying if you throw a die, what number you expect? Like is it 1, 2, 3, 4, 5, 6, and then if you take the average according to the like probability weights, that is the expectation of y, that will be 3.5. Okay. Now, so this is all about, I want to talk about, just a basic stuff on discrete probability, and then let's move on to, some randomized algorithms. Okay. So what is randomized algorithm? So what is a deterministic algorithm? It is like, step-by-step instruction, and it will have an input X, and you expect an output Y that depends on X, right? In the case of shortest path, on graph, a graph is an input, and the output is like, distances between like if it is all pair shortest path, then distances between every pair, and the algorithm will be like, steps of how to compute it. Now, in the case of randomized algorithm, there is one more additional thing. It can toss, coins, and it has access to random bits. Or in other words, you can think that your algorithm is able to do coin tosses, and then based on that information and input, it can compute an output. Okay, so there are so because of this randomness, its behavior is not always good, in the sense, okay, so for the same input, you may be, if the coin tosses gives different, like if you're going to run on the same input, your algorithm, the random bits may change. So based on that, the output may change or its behavior may change. So it says that, okay, because of randomness, it may not be good always, but it will be good in most of the sense. In the following sense, there are two ways you can think. Output is not correct. So based on this randomness, output may be correct or may not be correct, but most of the time output is correct. Say 99% of the time, for every input, like you fix an input and you look for all the random bits, most of the time your algorithm is going to give you a correct output. But sometime it may not give, like say 1% of the time it may not give. Such algorithms are called Monte Carlo algorithms. Okay. And the other is like running time may not be, may not be fast. The output is always correct, but some of the random bits will give you, faster running time. Okay, and some of the random bits will make you, bad running time. Okay, so the running time varies, but output is always correct. But what you expect is most of the time the running time is small. Or in other words, you want to say that, the running time depends on the random bits, which means that running time is a random variable. Okay, output is correct. Okay, for input X, there is a very well-defined output for X, and that well-defined output will be outputting it. And but the running time will be different. Running time is different based on the random bit. So the running time is a random variable. So for that random variable, I can talk about expectation of that random variable. So what we will generally in a Las Vegas algorithm, what we do is expected running time is very good. Okay, so which means that sometimes the running time may be bad, but expected running time is very good. Okay, so there is a question. Sir, is Monte Carlo a class of algorithm because it have bit different? I don't know the reinforcement learning. What is the definition? In the randomized algorithm, if you look into any books of randomized algorithm, the definition is this one. Like the output is correct with good probability. Say in some books, say like output is correct with probability 3/4. Okay. And
I have
yeah.
so what is the advantage of having variable running time? Like if the output is always correct, like
What is the advantage of having variable running time? Okay. So
yeah,
the advantage of
yeah,
having variable running time is like, see, ideally you want your algorithm to output correct output as well as it run fast. Okay. So if you cannot achieve both of them, then somewhere you need to do a compromise, right? Okay. Now, so, but most of the time the algorithm runs fast, then also it is good, right? If like,
okay,
okay,
so
if you are going to run 99 times for a particular input and sorry, 100 times and 99 times, like it is going to give you a very good running time, then your algorithm run fast, most of the time. So we are concerned about running time. So if deterministically we cannot do like much faster than in a randomized way, if we can do like the expected running time is, if it is fast, then that is also good, right? Does
okay,
that answer
okay,
your question?
yeah.
There is a lot of noise and I'm not able to listen properly. Did you say after that something? Maybe you can type. Okay. So there are two kinds of algorithm. One is Monte Carlo and Las Vegas. Monte Carlo means output may not be correct always, or in other words, you can say like the output is correct with probability at least 3/4. That's it. Okay. And in the Las Vegas algorithm, output is always correct, but running time is a random variable, and we want the expected running time to be, fast. Okay. So first, what we will see is mostly what we will see is an algorithm like a randomized. Next, what we will see is a randomized quicksort algorithm. And that is an example of a Las Vegas algorithm. That means that it will give you, sorted list, okay, of numbers for an input list of numbers, and its expected running time will be fast. And later at the end, I will just show you, like I will just give you an example without proof, an algorithm for a Monte Carlo algorithm. Okay, so their output may not be correct always, but the running time is, a fixed, deterministic. It does not depend on random bits. Okay, so first, an example of a Las Vegas algorithm. Okay, which is randomized quicksort. Okay. Okay. So what is a normal quicksort? Does it picks a pivot element. Okay. So maybe it's picking the last element in the array as the pivot, and after picking this pivot element, it splits the graph into three subarrays. One, the leftmost subarray, the left subarray contains all the elements which are less than that pivot, and the middle subarray is the elements that is equal to the pivot. And if all the elements are distinct, that will be singleton, the pivot itself. And the right side, the right array, like right subarray will be like the elements which are larger than the pivot. And what you do, recursively sort the left subarray and the right subarray, and that's the order, right? And that order will give you a sorted order. And what is the worst case running time of quicksort? You all have studied it by now, right? What is the worst case running time of quicksort?
O n square.
Yeah, O of n square. And you might have then like average case running time of this is order n log n. Okay, so we will come to that. Okay, so in worst case it may be giving. So you may be get all the time if you're getting sometimes bad pivot, then you will be running O of n square. For example, like if your pivot selection is the last element and if the array is already sorted, then you are going to get this. Okay, this running time. And what is randomized? The steps are exactly similar, but only one difference. The first step, how to choose the pivot, that is different. What you do, uniformly at random, choose an element and make it as a pivot. Okay, and then you do this partition into 3 subarrays, and the leftmost you again recursively sort. Okay, when you recursively sort it, for that subarray you are going to do coin toss again to get a uniformly at random one element from that subarray, and there you do that sorting procedure. And similarly for the right subarray. Okay, so this is the difference. Okay, now, so as you all pointed out, quicksort can take omega n square time to sort. Say for example, if it is already sorted, and then the deterministic one may take order omega n square, assuming you are going to choose the pivot not in a clever way. Okay. Now what we see next is the following: randomized quicksort sort a given array of length n in order of n log n expected time. Okay. Now, how does it different from the average case analysis? Okay, here it is, right? In the average case analysis of quicksort, what it is? Okay, it depends on the input order. If your input order is not so bad, then your running time will be good. But if the input order is bad, like fully sorted array, no matter how many times you run, you are going to take n square time. But that is not the case with randomized quicksort. Okay, on every input, the randomized quicksort takes order n log n time. Even if you give sorted array, on average, in expectation, it will take order n log n. So this running time is decided by the random bits you decide, or like you have this randomly choosing pivot, right? And what is the outcome of that random process? It depends on that. Okay, and if you take average over that random bits, what you're going to get is order n log n. So if you take a randomized quicksort algorithm and you are going to run it that many times on a particular input, even if it is fully sorted, then it is in expectation it is going to run in order n log n time. Okay, and or in other words, you can say like doesn't matter what kind of input you give, there is a tiny probability that that input may take order n square time. Okay, now we will come to that analysis. How does randomized quicksort takes order n log n time? Okay, the time is depending on the number of comparisons you make, right? So number of like a constant times the number of comparisons. So we just need to bound the number of comparisons. So asymptotically, this will be like odd, order of number of comparisons. So let Q of A is the input array. Let Q of A be the number of comparisons done on an input array A. Notice that this Q of A is a random variable, because if you randomly choose a pivot which is, which does not split your array nicely, then the number of comparison will be different. If you're going to pick something which is in the, like happen to be in the middle, then it is going to take a, less number of comparisons. So the thing is like this QA is a random variable. It depends on your random process. Okay. Now, so Q of A is the number of comparison. It is a random variable. And now you define an event, Rij. Okay, what is this Rij? That event tells ith element is compared with jth element. Rij is the event that ith element is compared with jth element. Rank I element is compared with rank j element. What do I mean by rank I element? You sort your array. Like suppose you look into the sorted list, which element comes in the ith location? That is the rank I element. Okay, and rank j element is the jth element in the sorted list. Okay, so Rij is the event that these two elements, the rank I element is compared with the rank j element, and that is the event. Okay, now. So for various, random choices, Rij may happen. For some random choices, Rij may not happen. Okay. So Rij may happen, Rij may not happen. So, but Rij is a event. Okay. Now we can define a random variable, which is an indicator random variable, Xij. What do I mean by indicator random variable? Xij value will be equal to 1 if Rij happens, the event Rij happens, and 0 otherwise. That's why it is called indicator random variable. It is indicating the random, the event Rij. Xij indicates the event Rij. So Xij equal to 1 if Rij happens. That means rank I element is compared with rank j element. Then Xij equal to 1, otherwise it is 0. Okay. And now, okay, there is something called, linearity of expectation. I didn't mention it in the previous slide. What do I mean by linearity of expectation? Expected value of, suppose I have two random variables x and y, then expected value of x plus y is equal to expected value of x plus expected value of y. This is called linearity of expectation. So, what we want, expected number of comparisons, that is expectation of Q of A. And what is Q of A? The total number of comparisons. That is equal to summation of expected value of summation of Xij. Xij says Rij happens. Rij happens, that is equal to 1 if Rij happens. So the total number of comparisons, is equal to summation of Xij. And the expected value of that summation is equal to summation of expectation of Xij by linearity of expectation. And now, what is expectation of Xij? Expectation of Xij equal to 1 times probability of Rij plus 0 times probability of, not happening Rij, or like 1 minus probability of Rij. And that is equal to summation probability of Rij, I comma j varying. Okay, is that clear? So to do the expected number of comparisons, I just need to compute summation probability of Rij. So that's what we are going to compute next. Okay, so the moment I compute probability of Rij, we are done, right? So there are this many terms, or like then I need to compute this term. So I want to say this is my objective. This is what the number of comparison is. Okay. So Rij is the rank I element is compared with rank j element. Okay. Now, so we want to compute what is the probability of Rij. Now, take an example. Take an example. Suppose the input array is 7, 5, 9, 1, 3, 4, 8, 6. Okay. Now, what is the rank of 7? It is 6. Okay. If I sort, 1 comes first, so the rank of 1 is 1. And the second element will be 3, so the rank of 3 will be 2. And the third element will be 4, so rank of 4 is 3. And the fourth element will be 5, so the rank of 5 is 4. And the fifth element is 6, so the rank of 6 is 5, and which is the sixth element will be 7. So there are how many? And then eighth element will be 9. So the ranks are mentioned below. Now what is the probability of comparing 5 to 8? So what is the rank of 5? It is 4, and rank of 8, it is 7. And probability of 4, 7 is the probability that the element 5 is compared with the element 8. The notation clear. Probability of R47. The rank 4 element is 5 and the rank 7 element is 8. And probability of R47 is the probability of comparing 5 with 8 in your algorithm. Okay, now, okay, here is the one. Suppose, so fix, R47, which means that probability of comparing 5 with 8. Suppose you choose a pivot which is smaller than 5, which means that its rank is smaller than 4. That is, say rank 3. You choose rank 3. Then what happens in your steps of the algorithm? It will make, okay, the middle guy is 3, middle subarray is 3, and the left subarray contain all the elements less than 5, less than 3, which is also less than 5, and the right subarray will contain elements greater than 3, which actually contain both 5 and 8. So once I split this into 3, I will not compare 1 with 7, or something in the left subarray will not be compared with the right subarray or to the middle subarray. But if I choose, the rank 3, an element whose rank is less than 4, then both the elements whose rank is 4 and 7 will be moved to the right subarray. And in this sub problem, you may be comparing 5 and 8. Or in other words, if you choose rank 2, a pivot whose rank is 2, then the probability of comparing 5 and 8, or the probability of comparing the rank 4 element with the rank 7 element, will be moved to the subproblem, to the right subproblem. Okay, and suppose you choose a pivot whose rank is more than 8, then both 5 and 8 will be in the left subarray, and the decision of whether to compare 5 and 8 will be taken in the left subarray. Okay, so this will be pushed towards the left. Okay, and on the other hand, suppose you choose the pivot as rank, pivot is equal to 5, which is the rank 4th element, then definitely you will compare 5 with 8, because how do you make these 3 subarrays? 5 you will be comparing with all the other elements to make these 3 subarrays, and 8 will also be compared in that step, and after you do this comparison, you will get 3 subarrays, and 8 and 5 will be in two different subarrays, and they will no longer be compared again. So it may be compared, at most 1, and that comparison happens when you choose a rank 4 element as the pivot, which is the 5 as the pivot. And that is actually the same case when you choose 8 as the pivot, rank 7 element as the pivot. Then you compare 5 with 8, and then you will make 3 subarrays. 8 is in the middle and 5 goes to the left, and they no longer will be compared. On the other hand, what happens if you choose 6 as the pivot element? Will they be compared? Will your algorithm?
Different problems.
Yeah,
Sub-problems.
they will be in different sub-problems like 5 and 8, and there will not be any comparison between 5 and 8. So this will not be compared. Okay. So the point is, if you notice, if the first pivot between 4 to 7, look at the elements whose rank is 4, 5, 6, 7, and you will be choosing pivots, right, in different subproblems. And among these, if the first pivot is the rank 4 element or rank 7 element, then you will compare. Otherwise, it will be like if it is outside this rank, then it will be pushed to the subproblem. If you are going to choose a pivot among these elements from 4 to 7 rank elements that is not 4 or 7, then they will never be compared. So what is the probability that you among these elements from I to j, which is 4 to 7, 4 is I, j is 7, among these elements, which one choose the first? If you choose that is the ith or jth or the 4th or the 7th, then it will be compared, otherwise it will not be compared. Okay, because of that, you can write Rij happens if and only if the following hold. Look at suppose ith or jth ranked element is the first pivot out of the elements ranked I to j, then that will be compared. And if you are going to choose some other element as the pivot, as the first pivot among these I to j elements, that will not be compared. So what is the probability that you are going to pick I or j among these I to j? If I look into the pivot selection, look at the elements whose rank is I to j. If the first one is I or j, then this will be compared. What is that probability? What is the probability of Rij? Because of this, what is written in the box? How many elements are there, whose rank is between I and j?
J minus I plus 1.
J minus I plus 1. And how many of them are like actually bad in the sense will lead to comparison? Or like how many of them, like it is 2, right? One is I and one is j. So 2 by j minus I plus 1. That is the probability that Rij happens. Is that clear? Yes. Okay. So the probability of Rij is equal to 2 by j minus I plus 1. Okay, good. So this I explained. Okay, now this is just formal way of writing it. Okay. So whatever I explained, that is it. Okay, this is the formal writing of it. Okay, now what I want to prove, like notice that I want to output expected number of comparison, expectation of Q of A, and by linearity of expectation and using the fact that xij's are indicator random variables, we got that it is equal to summation probability that Rij. Okay. And what is this? Rij equal to 2 by j minus I plus 1. That's what we proved. And so you take 2 outside, you can write it as I going from 1 to n minus 1 and j greater than I and j is at most n, 1 by j minus I plus 1. And this you can write like this, okay? What is the difference between I and j? Okay, then it will be delta going from 2 to n minus I plus 1, 1 by delta, okay? Just taking j minus I plus 1 equal to delta. You just take j minus I plus 1 equal to delta, and accordingly you just change the value, like, what is varying in the summation, you will get this. And do you know about the summation 1 plus 1 by 1 plus 1 by 2 plus, sorry, 1 plus 1 by 1 plus 1 by 2 plus 1 by 3 plus etc. Or like, sorry, 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus etc. That series, have you seen?
The Euler constant.
1 by n, is it a constant?
Minus log n. That
It
will
is
be a
log
constant.
n.
Yeah.
Sorry. So you may be talking about the geometric series. I'm not talking about the geometric series. It is, 1 plus 1 by 2 plus 1 by 3 plus 1 by 4
Yeah.
plus 1 by, okay.
Yeah, that is log n. Yeah. O of log n.
That is, if you go with till 1 by n, that is called harmonic series. Okay. So Hn is equal to, 1 plus 1 by 2 plus 1 by 3 plus 1 by 4, etc. Okay. And you can try to prove that is, that will be this number, fourth one, theta of log n. Okay. Or order of log. The proof is not very, it's a very simple puzzle. You can try to prove it. Okay. And this quantity is theta of log n. And because of that, how much it will be? So Hn is log n. How many times you will be summing up? At most n times, right? Like exactly n times. So this is upper bounded by 2 times theta of log n. And that is order n log n. So n times, and each Hn is order log n. And so this will be order n log n. So we got that expected number of comparisons of a quicksort is order n log n. And the expectation is over the random bits, so it does not depend on the input. Doesn't matter which kind of input you give. There is nothing called good input or bad input. But for the normal quicksort, there is something called good input or bad input. If it is fully sorted, it is a bad input for the normal quicksort. But here, no such notion, because you do randomness and make, things different. Okay. Now comes to how do we analyze this Las Vegas algorithm? So you have seen how we analyze it, right? We analyze the expected running time. Okay. Now how does it is different from the deterministic algorithm analysis? Okay. Now suppose I have a deterministic algorithm Q for a problem pi. Okay. Let Q of x be the time for Q to run on an input x of length mod x. Then how we define the worst case running time of my algorithm is T of n is equal to maximum of Q of x, where x is of length n, right? So you look for all the inputs of length n, and what is the maximum running time on any of these input you can have, and that is what your worst case analysis. Okay, worst case running time. And on the other hand, how does the average case analysis work? Okay, you are going to assume some probability distribution on the input. Okay, or in other words, like in the normal quicksort average case analysis, what we assume is a uniform distribution. Every input is equally likely. Okay, some probability distribution we assume, and then analyze the algorithm over the average over the distribution over the input. Or in other words, what you do is you fix an n, you take all the inputs of length n, and then you take sum of it and then divide it by or number of input. That you can do if it is finite. If it is not finite, then there is some kind of a a probability weight associated with the different kinds of input, okay, of length n. In the case of quicksort, you can think that, okay, like if the permutations are identical, then they have the same they are same, and then you try to take average performance over the input distribution. So average case analysis is like average over the inputs. Okay, and the worst case is the worst among the inputs of length n. That is what T of n. Okay. Now on the other hand, how do we analyze the Las Vegas algorithm. Okay. Suppose it is a randomized algorithm R for a problem pi, and let R of X be the time for, it is not for Q. Okay, sorry for the typo. It is for R. R to run on the input X of length mod X. Then R of X is a random variable. The running time depends on the coin tosses or the random bits. Okay, it depends on the random bits used by the algorithm. And what we do is we compute expectation, like what is the quantity expectation of R of X is the expected running time for X on input X. Now, how do we say that the worst case analysis? How do we do expected time on the worst input of length n? That is what the worst case analysis here. So, which means that T of n is equal to maximum expected running time of over the inputs of length n. Maximum expected running time over the inputs of length n. Is the definitions clear? Like deterministic worst case analysis, average case analysis, and in Las Vegas, what is the quantity we are interested in? T of n is the maximum expected running time for the over the inputs of length n. Is this definition clear?
Yes, sir.
Okay, thank you. Okay, now this is what an example of a Las Vegas algorithm. Okay, now I will not give a proof, but I will give you an algorithm which is a Monte Carlo algorithm, and this is the following. Given three matrices A, B, C, and you want to test whether AB equal to C. Okay, so we assume that all of them are n times n matrices. Okay, so three matrices are given A, B, C, and you want to test AB equal to C. One way to do is like you just multiply A and B, and then you compare each element one by one. And a simple, school mathematics will give you the running time A times B, multiplying A and B to be order n cubed. And there is a complicated algorithm which runs in much better than n cubed, that is order n to the power 2.373. Okay. And here is a very simple algorithm, okay, to test whether this holds, AB equal to C holds. Okay, so you just pick a random binary matrix, not binary matrix, binary vector, okay, of length n, okay, and call it R. And what you do is you just compute AB times R. How you can compute AB times R? First you compute B times R, and then you compute A times B times R. So B times R can be computed in n squared time, and then if you left multiply with A, that can also be computed in order n squared time. And similarly, you compute C times R, that can be computed in order n squared time. Notice that here the running time doesn't depend on which random vector you choose. Doesn't matter whether it is all like 0 1 1 0 1 0 1 0 1 or 1 0 1 0 1 0. It doesn't matter. It just running time is deterministic. It is order n square. Okay, but what you are going to do is you are going to output yes if ABR equal to CR. Okay, and it may not be true. Like you may get ABR equal to CR even if AB not equal to C. Okay, when AB equal to C, you are definitely going to get ABR equal to CR. Okay, but there is a chance that if ABR not equal to C, then your random vector will give you ABR equal to CR. But what you can prove is if AB not equal to C, then the algorithm will say yes with probability at most half, which means that the probability of failure is at most half. This you can try to prove by yourself. Okay, and what I want to say is look at this algorithm, and this algorithm till this much, okay, has a running time that does not depend on the random bit, but the output that depends on the random bit, and the output is correct with the probability at least half, and and not correct with the probability at most half. Okay, and there is a chance, like once you have such an algorithm, what you could do is you can repeat this algorithm 100 times. Repeat this algorithm 100 times, and then you can reduce the success probability to be at most, at least 1 minus 1 by 2 to the 100. Or in other words, you can decrease the failure probability to be 1 by 2 to the power 100. Because what you do, you run 100 times, and in all the 100 times, if it is going to give you equal AB R1 equal to CR1, AB R2 equal to CR2, then only you are going to say yes. So if AB not equal to C, then what is the probability that in all the time you are going to get, they are equal is like 1 by 2 times 1 by 2 times 1 by 2 times 100 times. Okay, so that will be 1 by 2 to the power 100. Okay, so this algorithm, it has, success probability very large, 1 minus 1 by 2 to the 100. But the running time is, a somewhat determinate. Like I would say like running time deterministic. It doesn't depend on random bits. Okay. And here is the final slide. How do we analyze the Monte Carlo algorithms? Suppose M is a randomized algorithm, a Monte Carlo algorithm on pi, and then M of x is the running time on the input of length mod x. It does not depend on the random variable. Okay, or in other words, it is the max over M of x comma r. So, or you think that it does not depend on the random bits, like which random bit it comes from. Okay? So it is, the running time is deterministic. It is like the worst running time on an input of length n. That is what T of n is. But on the other hand, what does this random variable, random bits affect? It is the output. So probability of x be the probability that m is correct on the input x. And how do we analyze that? So P of n, the probability of success on the inputs of length n, to be the minimum probability over minimum probability of success over the inputs of length n. Because we want to say that, with at least this much probability, this is going to, you are going to get a correct output. And with that, I will stop. Let me know if you have any questions. Okay, then see you tomorrow. So not tutorial today, so that's a message. Thank you.